in the previous sections, we were trying to build the various neural networks using the neural network toolbox, which is present under the machine learning toolbox of the MATLAB. So our first code was to create a neural network uh, that can classify the inputs into two categories. Okay, so you can see here input is defined as 1 till 6 and output is expected as 1 and 2. So we expect, right, 6 input layers and 1 output layer, right? So 1 to 6 all will go as a single as an input to a single neuron. So you can see that in the network we designed over here, you can see that one input and right the connections are uh, provided such a way that two outputs, and these are the connections, right? Connections, bias, weights, etc. we have defined. All right. So then we modified our designed neural network in such a way that the input size, the hidden layer size was 5, right? We made sure that there are 5 neurons in that, and we changed the default activation function into the log seq. Okay, so that's the meaning of this. Then we also have something like the configuration. So in the configuration, you can see that, right? We try to configure the neural network as per this, as per these inputs, outputs, and the defined neural network. Okay, then we also have what is called as the initial output calculation. We pass the input as it is to a untrained neural network to get the initial output, right? So this initial OP is the variable to get that out. Okay, then uh, we also have the another calculation that is after the training. So we'll perform the training now, right? And then we'll check what happens to the output. So my ANN is training function. It's ln Lavenberg-Marquardt. Performance is done using what is called as the MSE, mean square error. And also we have what is called as the train, used to train as a training function, right? So train my neural network with this input, this is the target, right? So my ANN will hold the values of the trained neural network. All right, and then you see we have the final output, that is my ANN of the input, right? So final output can be seen there. Okay, so let's run this to check what happens in the output. So initial output, you can see 0, 0 because it is not a trained neural network, right? But after the training, the final output comes, right? According to our code, you can see that the final output is after the training process, right? It is 1 and 2, and you can see that our output was defined as 1, 2. I wanted to get that output, right? But initially it was not giving that output because it was not trained. The weights were not optimized, but now you can see that, yes. All right, then let's move further. All right, then uh, let's move to the next one. So we also wrote another code that is to design the perceptron classifier. I'll share it once again. Okay, is it visible now? So uh, we wrote another code here to design a perceptron classifier, right? And here we wanted to generate some linearly classifiable data, and we wanted to check that whether this kind of neural networks we build is capable of, right, classifying such data sets, right? So you can see here we wanted 50 samples in each classes, and we wanted to have a offset value of 10 between the two classes just to separate the classes. Okay, now we created two variables. One is the required input and one is the output. So inputs were created in such a way that they are random numbers, right? 2 rows, 50 columns, right? And this is for the first class, right? Class number 1. And class number 2, you see we created another random samples, another set of random samples, rand n, 2 comma number of samples, that is 2 comma 50, right, plus an offset value. Okay, so that offset value, right, separates the class 1 from class 2 by adding that 10 value, 10 to the 10 to each of the values present in the second set. I'll show you that when we run this. Okay, let's move further. Next, we create the output, wherein I just have to tell that, okay, if any data that comes from this set, I have to classify that as zeros, right? You know that we can create zeros of 1 comma of samples. Similarly, right, for the second class, output should be 1. So it is ones of 1 comma number of samples, right? So I have 50 number of zeros created here and 50 number of ones created. So total 100, right? How towards the total size of our sample data set, that's 100, out of which 50 are belonging to class 0, 50 more belonging to class 1. Hope that is fine, right? Now we try to plot this. So in order to plot, we have to call a function called plot PV, right? So plot the input and output create. Okay, this is a perceptron viewer, so it's a plot PV function. Then, so if you are going for the neural network classifier, wherein the neural network is a perceptron, then it is pretty straightforward and easy to define and configure in MATLAB. It's because you have to call by its name, right? And that is, it's simply you call it as perceptron. So define your neural network as simply perceptron. It creates a perceptron class internally and assigns that to this particular variable name. Now you can call it by train this neural network with this input and this output. Once again, once you have the final results, the optimized weights, biases, and the parameters of the neural network get saved in my ANN. So, right, you have an option to view. Anyway, if initially we saw, but later on I made it as a comment because I don't want many figures to pop up simultaneously. I just wanted to see my plot PC, right? So this is the command to view the weight biases as in the, the optimized weights and biases plotted upon our data sets. Okay, so the IW stands for the weight and B for the bias, right? So whenever I say plot PC, it creates a straight line, and that straight line will be overlapped over the previously plotted data set, right? And it will create a straight line by using the weights and the biases. So how the weights and biases can be used to get a straight line, we have done that in the theory class of the fundamentals of neural network. Okay, directly apply that formula, you get a straight line. So that straight line is created internally by the MATLAB function plot PC, and it will plot it over the previously plot what you call the data set. All right, so let's run this. So you can see that there is a there are two classes, right? Each class has 50 samples, and there is a straight line which has been plotted, right, as a final result. So that straight line is a classifier. right? Anything that is to the right side of that straight line belongs to the class which is denoted as plus symbols. Anything to the left will be the other class which is denoted by zeros. Okay, so this is using this we learned how to code the perceptron classifier, how to perform the classification of a linearly separable class, and how to visualize the results, right? So those things we studied in our second code. Then we moved on to the third code, right? Here we wanted to uh, slightly uh, we wanted to solve slightly complicated problem of linearly separable classes by making the number of classes equal to 4. So when we have 4 classes, it's obvious that you cannot use a single line to classify, right? So in the simplest case, right, we need at least 2 straight lines. So our intention now becomes to verify whether we can make the perceptron classifier to decide what are the 2 straight lines that are required to classify the 4 classes. Okay, so this is our objective in this particular program. Okay, right. Now let's move further. So initial objective still remains same. You have to define the classes because there is no predefined data set available for such simple cases, right? So we have to make our own data set, right? So what we did now, so we wanted 50 samples in each of the classes, right? And we defined an offset value of 0.75 between the classes. Now, so we created classes, right, like this. So the class A, we defined 4 classes. You can see here class A, B, C, and D. So class A is nothing but it's a randomly generated numbers, one row, so many columns, minus offset. Okay, minus offset means, right, whatever value you get minus 0.75, right? And the next one, it's below that I'm creating another row, right, that is rand of uh, you can see that this is 1 comma number of samples per class, that's 1 comma 50 plus offset. So you can see how we define 4 different classes. That's just because either plus my here the first class you can see plus offset minus offset, next is plus plus, then you have plus minus, then you have minus minus. Other than that, no difference. So right, by adding or subtracting the offsets in various possible ways, we try to create the different classes. Very simple. You can actually, there is no strict rule saying that you have to do like this only, right? You can use any other possible method, right, that we have studied in fundamentals of mathematics, right, to generate these classes. Okay, fine. So somehow we created the classes. I will show you when we plot it. Then the next objective is to plot. So whatever we have created here, I wanted to plot. So first one is a plot of a class A, right? Then I put the grids and the hold on because I want to plot all the other 3 classes on the same graph. Okay. So I wanted to improve the readability of the graph by turning on the grids. That's all. All right. So that's what is happening here. Now let's run one by one to see this. So this is, I run the selection and advance. I run the selection. So you can see on the workspace which is present on the left side, we can see that class A, B, C are created. Each class has 2 rows, 50 columns. I'll just open one of them just to see this. Okay, so you can see that there are total 100 points, but total 100 samples. Each point has 2 values, x and y coordinate. That's why totally we have 50. Okay, so like this we have different classes. 4 different classes created. Now let me move further. So when I run this, you can see that, right, there are 4 different classes of uh, 4 different classes of this data samples have been created like this. All right. Then now I define what is my input and what is my target, right? Because you see there are 4 classes, so a single bit cannot represent 4 classes because a 1 bit can change 0 or 1. So that can represent only 2 classes. So when I want 4 classes, I don't have any other option but to increase my number of bits in my output to 2, because 2 raised to the power 2 is 4. Definitely using 2 bits, you can represent 4 outputs. So output for A is 0, 1, output for B is 1, 1, output for C is 1, 0, output for D is 0, 0. This is what we define. is it to it has to be the same thing or not? No, you can change. All right, so definitely output. Anyway, these 4-bit representation should be there for any of the classes, right? You can shuffle. All right. Sorry. Now, all classes inputs, let me try to define by concatenating horizontally all the data, right? So for A, B, C, and D, 4 classes data set, whatever we had created, I'll concatenate one after the other. So input all classes I'll run and I'll show you now. So it will be the concatenation. Then the targets. So I just try to repeat output A 1 comma. So 1 has to be repeated so many times, right? So many. This is the number of rows, number of columns, length of this. So I have to repeat. So that's my target, right? So whenever the input comes like this, right? Input is from class A. I have to get the output corresponding to class A repeated how many times? 1 row, so many columns. Whenever the input is from class B, I have to have output of that B class, that is 1 1, repeated 1 comma length of B times. So 1 comma 50, like that. I just expect this in my output. So let's check that. So what are the variables? One variable is input all classes. So 50 in each class, you can see that 50 into 4, so 200. So first 50 are from class 1. Okay, you can see that this still here is the class 1. Then the class 2 starts, class B, right? 50 till 100. So once I reach 100, till 100 it is class B. Then you can see class C. There is positive, negative, positive, negative, positive, negative. So till 100 it is both are positive, 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 and so on. Like that I can go ahead and make another separation at 150. So you can see that 150 till here it is, right? Plus, 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 minus, like that. Now I have both minus, minus. This is the other class, like that. So we have different values present. And the next output next variable we created was a target. So let's look at the targets. Again, it's 2 into 200. So you see all the first class data belonging to the first class up to 50, right? It is 0 1. Whenever it becomes class B data or class 1, it is 1 1 1 1. All become 1. This repeats till 100. So 101 onwards, it is 1 0. Okay, and the last after 150, you can see at 151 onwards, 0 0. So that's how we define the outputs corresponding to the 4 different classes. Okay, done. Then let's move further. Now in the next part of this code or next cell, we are going to design the neural network and we try to perform the training of that. So I define my neural network is equal to the perceptron. I just want to create a perceptron, right? So we begin with the e value as 1 and initialize the right adaptation parameters. The number of passes is equal to 1, right? So again, I create a line handle because I just in this case I want to show you another way of coding wherein you will initialize the weights of the neural network and the bias of the neural network, because of which you will get a straight line. Because I know that if I have a weight and the if you have a weight and the bias value of a neural network, using that we can definitely plot a straight line initially. Okay, once you have a straight line, now our objective in this coding is that I will, as soon as I have initialized the neural network's weights and biases, I will plot a straight line. But later on, when the neural network learns, okay, or whenever the neural network gets trained, our objective is that I keep plotting the updated way, the straight line that is also getting updated according to the updated weights and the biases. So that's my objective. So you see, I create a line handle here, and this line handle uses the plot PC function. So IW for the weights and B for the bias of a layer I'm trying to plot. Okay, so I create n is equal to 0. This holds the count for the learning process or the number of iterations. Okay, so n equal to 0, while the SSE, this is the sum of the squared error of E, and this n is less than, you can keep a lesser value here. The number of epochs required to get trained is very less, like within 1000 it gets done. But I kept it a larger value here just to show that the weight updation the looks like a continuous process for us. Otherwise, if I keep 1000 as my value, the weight updation happens instantaneously. We don't see an updation. Okay, so just for that purpose, I have increased this. Okay, so then once I enter into this while loop, increment the counter. This is the counter for the number of epochs, right? So whenever you enter inside this loop, once you perform these steps, okay, this is the updation and this is the plotting of that particular uh, line handle which we have created in terms of the plot PC, right? So I call draw now because within this loop I just want to draw, otherwise it will draw only at the end. So once this whole loop is finished, like either the sum squared of error becomes 0. If this is 0, this AND function, right, is AND becomes false. So whenever it is false, it will not fall inside the loop again, it will jump out of the. Otherwise, if the number of this, right, whenever this both will happen, only then only it will come. Okay, whenever both are satisfied, it will enter the loop. One of them fails, it will come out. So sum of the squared error is not 0, but the number of iterations crossed 1 lakh, then also it will come out. So that's my logic. Okay, you finish once you come out of this loop. So our objective now is to test whatever the training that has happened so far. We want to test. So generate a test input randomly, right? And y is equal to pass that test input to the net, which is a trained network. So you can see that net which is defined here is the trained network. So to that network you pass your input. So input will be evaluated by the network to provide an output which comes at the output. Okay, so that's the simple program. Let's try to see here. So you can see that these values are okay. I think I made the thing visible. Okay, now observe the graph when it runs. Okay, so initially you will have the straight lines at some other location, but as the time progresses, they will come and occupy the final positions, right? I'll run this once again. Observe this carefully. Yeah, so initially the graph not visible. All right, let me just check what I can do. Now, how about now? Oh, just hold on. I'll make the graph visible. I'll try to reset. It's coming right now. Oh, okay. Now I'll run this code once again. Right, observe that initially, right, the position of the straight lines were somewhat far away from these positions, right? And when this runs, when the code finishes the execution, right, you can see them reaching their final positions. I'll run once again for, yeah. Can you did you observe that? Right? Initially they are at some other location. I'll run once again. I'll run once again. So now you see they're actually located at different positions, but when as the time progresses, they will come and occupy these locations. Correct? We'll run again. Just Yeah, I can see. There is a figure which is being displayed on my screen, but I think it's not coming. I'll try doing that once again. I'm trying to bring the MATLAB figure. It's visible now. Now I'll run once again. Just check whether anything happens. Okay, so it's coming, right? Can you see? Moment you cannot see. Okay, let me. So it's actually for a fraction of second. By the time it comes, I think the moment is over. I'll try to run once again. I'll close this. Now you try to observe. Could you see? No. I'll run again. Could you see? Only maybe 0.25 seconds or something. The, at the very initial moment, you should be able to see that. I'll run again. Yeah, I'll run again. Now you see. Originally, the straight lines are at some other location, but as the time progresses, it will come to that location, right? I'll run again, right? So if you have seen, you tell me, otherwise I keep running. Okay. Now, yeah, it will run initially, and then it will display the movement of the straight lines, and straight lines come to their optimum position at the end, right? So did you see the movement of straight line at least for maybe a very less fraction of second? You could see, you could see that. Okay, all right. That's what our motto was regarding this program. Okay, now I will show you how to define and construct a slightly advanced neural network to classify a different type of data set. Okay, so what if I want to classify sine, cosine waves which are not linear, right? So the class will become non-linear now. So maybe the perceptrons become too simple to classify. So our intention now is to go ahead and calculate something different, right? So classify something different. So I'll go ahead and create a new neural network. Okay, so let me edit a new script now. I custom ANN4. Okay, now, so what we do now will perform what is called as ADALINE. This is Adaline. The neural network which we are going to design is a Adaline neural network. Okay, and we want to perform a time series prediction. Okay, this is what we want to do. There is a signal which is going to vary with time, right? And I want the neural network to predict what's going to happen with that sequence, right? Whichever is a time varying sequence I'm going to give as input. What happens next? I want a predictor now. Okay, right. So my intention is to construct a something like an Adaline neural network for adaptive prediction of the time series. So I can write time series, it's an adaptive prediction. Okay, close all CLC. Okay, so these are the prerequisites before we go ahead in any of with any of the coding, right? So what I do, I define the time. Now I will define the time now. Okay, so this is okay. I'll write definitions and initialization of various parameters we require for this code. Okay, so first I'll define a small time, right? So time gap between the samples. Now I can say 1 second, which means the samples have a gap of 1 second between them. At a particular point t equal to 0, I receive one sample, but my next sample comes after 1 second. So in 1 minute, you get only 60 samples. It is too difficult to visualize. So we cannot go with that because machines are capable of handling much larger or much faster data. So I'll keep the duration of one sample to be 0.01, which means this is second, 0.01 second for one sample, which means in one sample, 1 second, you can have 100 samples. This is what is my definition. I try to define an initialize like this. Okay, then let's create a time interval. So T1 is equal to, I want to start with the say 0, and I want to go till, I want to have an increment of dt that is 0.01, and I want to go till say 3 seconds. This is my first time interval. I also define another time interval, say T2. Okay, so T2 is my second time interval, and now you see I want to start from after 3. So 3 is already defined, so I'll perform 3 plus the dt colon, and I want to have the same increment dt, and I want to go till say 6 seconds. Okay, so total duration I defined is 6 seconds, but I want to create an array now. So time axis t is equal to, put it concatenate the total time. So that is t, it should be t1 space t2. Now you see the t1s whatever created and t2 created comes under the same name, that is called t. Okay, so my time axis is over. Now I define a some sequence, some non-linear function. Okay, so I want to call that as y. So y is equal to, okay, let me create this using sine function. Say 1 will be a sine function. Okay, so this is sine of some random number I'm going to put. So 4.1 times, uh, maybe I'll put a pi. Omega t is what I require. Okay, so time is, for the first half I'll use t1. This is my first sequence, sine omega t. And the second function, I'll try to keep it a different one. Maybe this is a 0.8 into, maybe I'll use a cos function. Let's see, 0.8 cos 8.668 in this into pi into say t2. Let me just check whether I enter this correctly. Yeah, so I can close the square bracket so that this becomes an array. All right, so let's first plot what is going to happen. Let's try to plot. Okay, so which is a command to plot a simple graph. It's a plot function, plot. You have to specify what is your x-axis. So x-axis is time, so defined as t. Y-axis is the amplitude, so that is defined as y. I also request MATLAB to plot the specific pattern. So I want dot and dash to be right. The plot should be like this. This is what I'm expecting, and I'll put the maybe the plot this and make grids visible. Okay, let's try to run this. Okay, yeah, you can see the screen, right? The figure comes up, pops up, and you can see that yeah, so first half still 3 seconds, it's a bigger graph, then it's a different graph, right? Then it's a smaller graph because we use two different graphs over here. First one is sine of something into this, second is this. I'll try to reduce this, maybe I'll make it smaller. So 0.4, let's see. Okay, now yeah, it looks more much. Okay, fine. So this is what is the plot. Okay, now I don't want this to be created manually. My expectation is slightly different. I want the neural network to predict that, okay, at t equal to 3 seconds, something like some changes is going to happen and it has to plot this, not the continuation of this. Okay, let's try to make sure that machine understands this requirement. All right, okay, let's see. So now what I do, I directly go for uh, yeah, I'll convert this into the sequence, right? So I'll create that as, say, P. Okay, so let me create. This is a data preparation part, right? I want the sequential vectors, right? I want this data, the sequence, to be converted into what is called as the vector. Okay, so let's try to do that now. So in the next section, I'll try to call, say, P is my sequence. I want a time sequence. So you can see that this output is a time sequence. One after the other, the sample keeps coming. So we have the requirement of the concurrent vector. All right. So the function, there is a function called con to, it's a vector getting converted into the sequences, okay, of this y. So I cannot give the y as input. That's why I have to make this conversion. Okay, once this is done, now let us define the neural network. Okay, now you see the neural network which we are designing now should be capable to it should be able to predict the next value of the target signal. So what we do, we try to give some amount of delay over there so that the machine is able to handle that. Machine is able to do some calculation. So what we do, I define input delay. So let me assume some delay here. So let's define this delay as 1 till, starting from 1 till. So delayed inputs to be used are this. And then I also define the learning rate. Let's keep it small and let's try with the smaller value. Later on we can modify if required. Okay, directly define the Adaline network now. So the net is equal to, so in order to define a Adaline neural network, I have to perform what is called as the linear layer as the function. So linear layer of, so define, so what are the parameters we have? Input delay. So you have the input delay here, and I also have to give an input that is, what is the learning rate? Learning rate. I define this, and once you do that, once you have defined your neural network, you have to tell the machine that, okay, what is the learning rule that you want to apply so that this gets trained. Okay, Right. So we directly start with the training now. So the training updates the net, comma. It also provides a value variable y and an error represented by e. So you can give any names over here, doesn't matter. Okay, comma. Tell which learning rule, adapt. Okay, so this is because I want to apply the adaptive learning rule. So what are your inputs? I pass the network to this. My input is P and my target is also P, right? Machine has to learn how to get the P ultimately. Okay, P as the output. P in the sense it's a time sequence. The Y which we had plotted earlier, I just want now. So, okay, let me, you have an option here. I'll make it optional. So, view net if required. Okay, so anyway, it's of no importance for me. I don't need that. Okay, I also want to look at the updated weights and biases, so I can go for this. So specify what you want to see. Okay, uh, weights and bias after learning. So I want to visualize net dot. I know that weight is IW of 1. Then what do you want to see? Want to see the bias. Okay, mistake here. This has to be the flower bracket. Okay, the braces. And net dot, it's B of 1. Okay, I can see the neural network that's getting trained. So weights and biases will be able to see this. Okay, now I want to plot my final answer. In a sense, you can see that when the machine is learning with the input, right, I should be able to plot the output also, right? Because I give an input, which is a time series, initial 3 seconds, one, what you call, one function, then after 3 seconds, it's a different function. When the input changes, like all of a sudden there is a transition from the 3 seconds, at the end of 3 seconds, there is a transition from bigger amplitude to a smaller amplitude. Even the machine will not be able to do that prediction immediately. It takes some time. So I want to show you that this is what is going to happen. All right. Now I have a time sequence. I want to convert this back to the plottable or the viewable values. All right. So Y and E are the actual outputs that comes from the network. Y represents the output, E represents the error. So let's do one thing. Okay, let's try to convert this. So Y is equal to, I'll do the reverse. Previously, you see P is equal to, the small letter P is equal to, right, con to sequence, right, converted the continuous variables into the sequences. Now I have the sequences available with us. I want to convert it back. So this is sequence to con of itself. So I'll call this is Y. So Y is equal to of this, and I want to take only one dimension from that. So I can write Y is equal to, okay, let's check what happens now. So far, let's try to run this. Will it run or is there any error? No. As far as the output is considered, no error. Okay, fine. Now you see the Y is actually a cell, right? Inside this cell, I have 600 component samples. Okay, but I don't want that. I want to convert this into, you see the P, right? P is actually a cell. So P was a cell. But now you see, I want to convert this Y back to the sequence. So I can write Y is equal to Y of 1. So there is only one cell. Now you see what happens if I run this. It's not small one, sorry, it's a capital one. So observe now, so far the Y is a 1 into 1 cell and this is the Rx value. Okay, I'll run this once now so that it becomes a sequence. Now you see the y becomes, just see the y has been converted back into the, right, the samples form. So that's what we did by doing this. Similarly, I need to do the same thing with the error. So E is equal to, so this error is the error of the neural network. When it learned, it observed that, okay, there is this much error, right? So that error is what is the E, right? E is equal to sequence 2 of E. So this actually generates a cell. Again, I don't want a cell, I want E to be the sequence. So capital E of 1. Now this actually puts the error as well. Error also in the same format. Let's try to run this. Yeah, it runs. Okay, till E is done. Now my intention is simply to plot. Okay, I'll plot two things now. One is the error and one is the output and error, right? So let's go with the, what you call, okay, I don't want this output anymore. Okay, so I'll suppress this. I'll make this comment so that I don't see this output anymore. Okay, then I call a figure. Then let's say I want a subplot now. So subplot 2 rows, 1 column, first graph. Okay, 2, 1, 1. I want to plot two things now. Whatever was plotted earlier, I will include that here. So that is t, comma y, comma. I think we try to. Okay, I'll give a color now. So simply maybe blue color. That's the first graph. I can include the second graph as well here. So that is time versus my predicted output. That is y. And let's change the color for this, and let's change the values as well. Okay, so what I want this to be red dash dash. Okay, let me check whether this works. Okay, so that's the plot. Okay, and let's give a legend so that we don't confuse when we see the graph. Legend, what's the first one? First one is original. Okay, and the second graph is the predicted graph. Okay, single code. Okay, it will print, right? Again, I can definitely put this. I just want to turn grid on. Okay, this is the first figure. Then subplot 2, 1, 2, right? 2 rows, 1 column, the second graph, right? I simply want to plot which one I want to plot? Time as my time axis, and I want to plot the error. So that is E. And you say different color. So, and maybe grid on for this. Let's see what happens. Okay. Something. Yeah, it cannot be. I cannot give a space. Maybe that's the error. Well, yeah. Okay, you can see that, right? There is a small difference between the blue colored line and the predicted line, which is a dot dot red, correct? So initially you see that machine takes some time to learn that, okay, this is the curve. But after maybe 1 second, you can see they coincide, right? Completely they are coinciding. Machine has learned, whoa, this is the equation I should use to plot. Okay, this is true until 3 seconds when there is a change in the curve. You see again there is a small gap between the red and the blue lines. Okay, Again, it takes some time to learn, maybe up to 3.2 seconds. Then you see that, yes, machine has learned that, right? So where is the error? Whichever points there is a difference between the actual value and the predicted value, you can see that now. So you see the predicted value and actual values vary like this initially up to first 1.5 seconds. Then there is no error. Error is 0. Okay, machine has learned properly here. Again, at 3 seconds, I know that my output, the wave which we are generating changes. Amplitude changes, frequency changes, because of which you see that there is a lot of, right, a huge error all of a sudden at 3. But very next moment you can see that error reduced, keeps on reducing, and error keeps coming to 0. Okay, so this is another way of showing that machine can predict what's going to happen next. All right, so some of the requirement in terms of the representation of data, I cannot give the data as it is. I have to convert it into a sequence when I give input, and when output comes, it comes in the format of a cell. You have to convert it back into the sequence. This is the change that has to be done as a prerequisite to train a machine for data sequence, right? That's a very important concept, right? Other than that, everything is very same, right? Like our previous codes, you can simply design the neural network, give an input, tell that you want to guess the same input, it becomes a predictor in that case. So what is the format for a predictor? For the format, the predictor is, you can say that the machine, I want to, this is my input and I want to predict the same. This becomes a predictor. Okay, so change you what all the things you can change here. You can change the learning rule. You know what are the learning rules possible, right? Also, you can use the help, MATLAB help, to see what are the options you have. In addition to the adapt, you can change, right? That's one thing. The input, the delay can be changed, learning rate can be changed, and you can make a lot of modifications here, right? Just to see what happens with the output ultimately. Okay, so maybe in the next session we will do one or two more exercises slightly complicated than this, right, wherein we try to classify say 4 non-linear classes. That's what is there in my mind. We'll see.